back to our study of derivatives. And today I'd like to talk a little bit about some of the motivation behind the development of calculus was to study particle motion problems. One of Sir Isaac Newton's problems he studied, again, was describing motion. And so I'd like to model a little motion and to talk about what I talk about here. Use this as, I think, a pretty good title: velocity and acceleration. Okay, that gives physical meaning to derivatives. So you get kind of a more of an intuitive feel. What do these rates of change mean? What do rates of change mean? When I'm talking about motion problems, I'm usually talking about derivatives with respect to time. How is a particle's position changing with time? So right up here, we talk about S. We got a function S of t, and we call it displacement. Maybe I even use the word position. Position. It's not distance now. Okay. Distance meaning it's always, distance would be always positive. I'm 10 miles from home. But a displacement, I could be 10 miles west of home, which I might call positive, or 10 miles east of home, where I would call negative. So a position could be positive or negative. Okay, and we're always going to, in this course, Calculus AB, we're going to talk about one-dimensional motion, straight line motion. So our position will always be just positive or negative. Okay. Then when we talk about, once we have a model, S of t, for position or displacement, we can find the velocity of the particle we get by taking the derivative. So the derivative just tells me how is my position changing with respect to time. That's going to be the velocity. And we'll talk about speed later. Speed is not velocity. Velocity, again, could be positive or negative. It tells me how I'm moving. Is my change of position positive or negative? Then acceleration is going to tell me, well, how is my velocity changing with time? And those do have physical meanings. Okay. So here's my little model here, and I can't, when I do this in the classroom, I usually walk in front of you, in front of the room, but I'm not going to do that on video here. So, but I'm going to model my motion. And at point A, notice I've got a function here of time. And at point A, I'm standing right in front of you. I'm standing right in front of you, and then I start walking to the right side of the room. Right side of the room. At B, I'm at the window. I'm at the window on the left. Then I kind of turn around, start walking back. At C, notice C is my position. C, I'm right back in the same position as A, you know, so many seconds later. D, I start then going to the other side of the room. Here I'm on the left window at D. D is left window. And E, I'm right back at the middle. So this is a model of my walk, and I'm walking over to the, I'd say, the right window here. I'm back in the middle. D, I'm at the left window. And I'm back at E. Notice I'm modeling my motion as a perfect sinusoid because I'm a pretty talented walker. And I've got 10 times the sine of t. Notice it's 10. 10 is my amplitude, because I'm going to say the width of this room, we're going to say is 10 feet. 20 feet, I guess. So this is, S of t is going to be, the units of this are going to be in feet. Okay, feet. Now, when I want to take then, if I want to find velocity in green, let me change my pen to green here. So this was S of t. This is V of t. And I drew these ahead of time to try to get these things right. But what is V of t? Well, V of t, I know above, the velocity is just equal to ds dt. And that's going to be what? Well, it's going to be 10 times the cosine of t. And that's what I tried to do here, 10 times the cosine of t. Notice my velocity here is positive. Velocity here is positive, but decreasing as I go from A to B. So I'm walking over to the window. I'm walking over to the window and I'm slowing down, right? Because at the window, I'm actually turning around. At B, I'm changing direction, walking back, and now I'm walking back over here to C, which I hit kind of my maximum velocity in the negative direction here. Okay, at C, I'm right back in the middle, right? C, I'm right back in the middle of the room here. Notice these little, these are supposed to be lined up in time. These are the same axis here. So at C, I'm in the middle of the room, but I'm moving, and I'm still moving to the left. Velocity is negative. Come back to D. At D, where I'm at the left window. See, at D, I'm at the left window. And what happens to my velocity? It's 0, because I'm turning around and going to point E. So notice I start at A. I'm moving pretty fast as I start up. I go to B. I kind of stop, turn around, go in the other direction at C. I'm maximum velocity walking to the left. At D, I hit the window, turn around, and then come back. Okay, I could also, if that's my velocity, A of t is what? Well, I know A of t is equal to dv dt, and I know that's equal to what? Well, that's going to be, I know how to take the derivative of this, right? Minus 10 times the sine of t. Let's put the units back on these things, because I think sometimes units will help you. Notice S of t is in feet, right? So I've got feet here in the numerator, and I got time in the denominator. So my velocity is in feet, and I'll just abbreviate it as you typically see, feet per second. Feet per second is going, that's a measure of velocity, feet per second. Now look at here. Here I've got what? Well, I've got velocity in the numerator, right? And I've got time in the denominator. So here, what's my units on acceleration? Well, it's feet per second. I'm going to move this thing over here a little bit. Feet per second per I did that. Like it was set to me. Feet per second per second. And you'll see the units of acceleration are indeed feet per second squared. Okay, so here we have a simple example of modeling walking here. Notice the position function, the velocity function is the derivative, and the acceleration function. And well, I'm going to ask you a few questions that you'll see, be able to work some motion problems. Okay, welcome back to our study of particle motion. And here I'm kind of putting the whole thing, a little bit of the whole thing together, in the fact that I've used a function to model my perfect motion, right? I'm modeling my position with this function here. I take the derivative of position, or derivative of displacement, to get my velocity. Kind of tell me how fast I'm moving and in one direction. Okay, it's got feet per second as units. Then I get, if I want acceleration, I mean, how fast is my velocity changing? I take the derivative of velocity. Now remember, acceleration, if you've studied physics yet, is related to directly proportional to force, or force is directly proportional to acceleration. So let me ask you a few questions that you would see here. First one here, when do I change direction? Remember, I'm walking across the room. When do I change direction? Well, I do that at time. I go to my velocity curve here. This is v of t. And I look, where does my velocity change direction? Is when I cross through the origin. So this is at B and D. Okay, what is the acceleration at the points above? Okay, what is my acceleration as I change direction? And you'll see here, acceleration at point B is at a maximum in the negative, so I got a maximum force. You think about the force that it's going to take for me to change direction, or any particle change direction. It's got to be working, it's negative here, and here my force at this point would be positive. So that's the acceleration at that point. What is the total distance from A to D? From A to D, well, in this case, from point A to D, notice A to B is what? I go to the window, that's 10 feet. And so this is the middle of the room. This is A to D, the distance, the total distance I traveled now. Notice what I did. I walked to the front of the room. That's 10. I walked to the right window. That's 10 feet. I walked back. That's 10 feet. That's 20 feet here. And then back to D, another 10 feet. That's 30 feet. You have to think about that motion. Eventually, we'll tell you about how to integrate in order to calculate that total distance. Okay. Now, from A to D, let's see. What is my displacement at E? What is my displacement at E? Well, at this point here, where am I? What's my position at E? Well, it's 0, right? I'm back at the origin. I start in the middle of the room. I go to the window at B, back to the middle, to the left window at D. My displacement is 0 here. Okay, speed. You'll get these questions. What is the speed? Speed, you have to know, is defined as the absolute value of velocity. So when we talked about when you're driving in your car, your speedometer never goes negative, does it? If you're traveling east on Broad Street or west on Broad Street, you're going to get the same reading. It gives you the absolute value. And maybe let me draw this in here for you. I'm going to draw speed. I think it's probably pretty good to see. I'm going to draw speed here on the velocity. Okay, notice this. Notice it never goes negative, so it's going to go like that. It's going to take the absolute value and flip this up, and then it's going to go like that. So this, in red, that's equal to speed. The sooner you learn that, the better off. That's the speed of time, okay? And it asks me, in what intervals is my speed increasing? Well, my speed, okay, so from A to B, the speed, I better get another pen here. From A to B, the speed's going down, okay? From B to C, oh, it's going up, isn't it? Speed is going from 0 to maximum. So from B to C, it's increasing, so I better write that down. B to C, in that interval, it's increasing. Now notice from C to D, it's decreasing, but from D to E, it's increasing. D to E. Oops, wrong spot. D to E. So I'm speeding up. I'm speeding up when I start speeding up when I turn around. When I turn around at the right window, I start speeding up till I hit the middle of the room right here and C. Then I start slowing down as I get to the left window before I turn around. Then I speed up from D to E as I go back to the center of the room.